Hello and welcome. Have you ever had an idea for an app or a program and just wondered, how does that actually become something a computer can run? Well, that's exactly what we're going to break down today. Let's get right into it.
So the big question is, how do we tell a computer what to do? I mean, they don't speak English, right? We're going to walk through exactly how it's done, and I promise it's way more straightforward than it sounds.
Okay, so where does this whole process even start? Well, believe it or not, every single program, every app on your phone, it all starts with one simple thing, a problem that needs solving. It's the whole reason for writing code in the first place.
This whole journey from an idea to a working program really boils down to three core steps. First, you've got the problem. Second, you have to design a plan. We call this an algorithm. And finally, you write the actual program. We're going to take a look at each of these one by one.
All right, let's talk about step 2, making a plan. This is absolutely crucial. Before you even think about writing a single line of code, you have to map out your solution. And this plan has a special name. It's called an algorithm. Think of it exactly like a blueprint for a house. You wouldn't just start nailing boards together, right? You need a plan first. Same idea here.
So what exactly is an algorithm? Don't let the fancy words scare you. It's just a set of specific steps to solve a problem. That's it. It has a start, it has an end, and it tells you what to do in between. The best analogy? A recipe. A recipe gives you step-by-step instructions to bake a cake, and an algorithm gives the computer step-by-step instructions to get a job done.
Now, a lot of the time, to make these plans easier to understand, programmers will sketch them out visually. And the tool for that is a flowchart. It's a fantastic way to actually see the flow of your logic and spot any tricky parts before you get lost in the code. And flowcharts have their own basic symbols, kind of like a visual language. You've got the oval, which is always your start and end point. Then there's the rectangle. That's for any action or calculation, like add two numbers. The parallelogram is for when you need to get info in or show info out. And the really important one, the diamond. That's for decisions, a yes or no question that changes what happens next.
Okay, so we've got our blueprint, our algorithm. Now we're ready for the fun part, actually writing the program. This is where we take that plan and turn it into a language the computer can finally read.
So a program is really just a collection of instructions, or statements, that are written in a specific programming language. And each one of those statements, it's basically one step from the algorithm we just designed, telling the computer precisely what it needs to do.
Here's a simple way to think about it. You and I communicate using a language, like English. Well, to communicate with a computer, you need to use a programming language. You've probably heard of some, like Python or Java. It's just a structured way for us to give our instructions so that there's absolutely no confusion.
Okay, so we know a program is made of statements. But what are the statements themselves made of? Let's zoom in a little closer and look at the real building blocks. I like to think of them as the Lego bricks of programming.
One of the most basic and most important building blocks you'll ever use is something called a variable. See, your program constantly needs to remember stuff, right? A variable is just how it does that. The best way to picture it is as a labeled box. You can create a box, stick a label on it like, say, player score, and then you can store a number in there to use whenever you need it.
Now, to get just a little technical for a second. Under the hood, a computer's memory is just a massive grid of cells, and each one has a super long, complicated address, kind of like a house number. Can you imagine trying to remember an address like 4 billion something? No way! And that's exactly why variables are a lifesaver. They let us give a simple, human-friendly name to one of those memory spots. So instead of that crazy number, we can just say player score. But there's one little rule with these boxes, or variables. Before you can use one, you have to tell the computer what type of stuff you're planning to store in it. Is it going to hold a number, or maybe just a single letter? This is what we call its data type. And you'll run into a few common data types over and over again. For example, if you want to store a whole number, like 10 or -5, you'd use an int, which stands for integer. If you need a number with a decimal point, like 3.14, that's a float. And if you just need to store one single letter or symbol, like the letter A, that's a char.
All right, let's recap. We have our problem, we have our plan, and we've written our program. We're so close, but there's one last super important step. The program we wrote is for humans to read. Now we need to translate it into the only language the computer's brain actually gets. And here's the thing. Even though we wrote our program in something like Python, the computer's processor, its brain, doesn't understand Python. It only understands one language, machine code. And that's literally just a long stream of ones and zeros. So we need something to act as a translator to bridge that gap for us.
Now, there are basically two types of translators that do this job. The first is a compiler. A compiler takes your entire program, reads it all in one go, and spits out a completely separate file that the computer can run directly. This is usually super fast. The other type is an interpreter. It goes through your code one line at a time, translating and running each line as it goes. It can be a little slower, but it makes finding errors a lot easier.
So let's put that whole picture together. Step 1, you write your program. That's called the source code. Step 2, a translator, whether it's a compiler or an interpreter, reads your code. And step 3, it creates the machine code, the ones and zeros that the computer's hardware can actually understand and execute.
And there you have it. That's the entire journey, from A to Z. We started with a simple problem. We made a logical plan, our algorithm. We wrote a program with clear instructions. And finally, we used a translator to turn it into something the computer can actually run. That, in a nutshell, is what programming is all about.
See? It's not magic at all, is it? It's just a series of really logical steps. And now that you know the path from a simple idea to a real set of instructions, it just leaves one question, doesn't it? What problem would you like to solve?